Our next presenter is Michael Otte. He's a assistant professor in the Department of Aerospace Engineering.
Awesome, thank you. So my lab is called the Motion and Teaming Lab, and today's talk is going to be kind of a two-part talk where first I'll talk about some robot motion stuff, and then I'll talk about some robot swarm stuff. And this is kind of highlighting some recent results of my students. The first thing that I'm going to talk about is work by Sharon Nayak, sitting right over there. This is bidirectional sampling-based motion planning without two-point boundary value problem solution. So a little bit of motivation for this. It's in kind of search problems, it's well known that if you have kind of the ability to do bidirectional search, then you can get significant speed improvements, even though like the big O runtime is essentially the same. If you're kind of, it's a volumetric kind of expansion, one way to think of that in a high dimensional configuration space. And once these two kind of expanding balls touch, then you're essentially done. And so the amount of volume contained in two balls of half a radius is much less than a single ball of a full radius. That's a very high level, sweeping tons of details under the rug why this is important. But when we have vehicles, they need to kind of get from one point to another. And one thing, when I took differential equations that I wish they had told me is that most of the vehicles that exist in the world, we can't solve their differential equations. We don't really know how to do it, or we have to use kind of very computationally complex numerical methods to do it. Now we can forward simulate often, which means that we can get starting at one point somewhere else, and we know where we might end up. But to kind of link 2 points is very challenging for a lot of robotics problems. So when you can't link two things up, doing bidirectional search all of a sudden becomes kind of hard or impossible. So this work is to kind of get the benefits of bidirectional search when you cannot solve the 2-point boundary value problem. And just to kind of, again, highlight what we're doing, what we're not doing. So unidirectional search kind of starts at a start and goes to the goal, or starts at the goal and goes back to the start. Bidirectional starts both at the same time and kind of grows together. And what we're doing is this other kind of bidirectional search thing, where we're using the reverse tree that starts at the goal and goes back to the toward the start as a focusing heuristic for the other tree. So once they get close to each other, the forward tree can grow very quickly to the goal. And here's kind of we have a video of this, I think, on the next slide. But basically, this slide is kind of summarizing what I already said. So let's see it in action. And we are going. Oh, we're not going. Okay, apologies for that. Let's see if we can do it. There we are. Okay, so we're growing very quickly, and once the trees meet, then we get very quickly to the goal, almost in much less time than it took for the trees to meet originally. Who remembers the quick key to start the slideshow from where I am? Shift F5, thank you. I appreciate that. So we also tested like a different idea. So in the first one, which we're calling GBRRT, we're accounting for the dynamics of the robot, both in the reverse tree and also in the forward tree, which helps if there's really weird kind of passageways that really you're really kind of pushing the dynamics to their max in order to like move around through narrow passages or something like that that are shaped in interesting ways that happen to be compatible with your robot. In other cases, you can just use kind of a very much more simple backward tree where it's essentially assuming like a point robot that moves in a holonomic fashion. And this can be useful in many systems, even though we're not explicitly considering the dynamics in the reverse tree. It still can be like a really good focusing heuristic for the forward tree. And yeah, there's that video. So don't pay any attention to the algorithm that's on the left side of the screen here. This is kind of the algorithm for the GBRT. We're just going to highlight the different regions that are involved in different parts of the search. There's kind of two important things that we need to make this work. One is we have to have the ability to be focused by the focusing heuristic, which means we need to bias growth along the tree in one way or another. And also these sampling-based motion planning algorithms usually have completeness guarantees in the form of probabilistic completeness, or essentially, as you sample more, the probability that you find a solution approaches 1 in the limit as the number of samples approaches infinity. But in order for that property to hold, we need kind of some nice sampling over the space where we have a dense kind of support for the sample distribution that's happening. And so we're going to use kind of alternate between these two things. And you can kind of, as long as you choose something that's not 0, not 1, this kind of exploitation ratio is how often are we like exploiting the focusing heuristic versus just random sampling. And then the delta radius is very similar to kind of any RRT. RRT is fairly well-known algorithm, but there's kind of some radius associated with that. And then down here, we have, for our particular kind of experimental implementation of this that we tested, the way that we did biasing is to kind of grow a few expansions and then pick the best one that got us most in the direction of the focusing heuristic. Now, if you had a different way to kind of focus your search using forward simulation, that would be also fine. So I've kind of made this a little bit lighter gray to say like, okay, in our specific implementation, we do this, but if you would just want to use this general idea, like you don't really have to worry about the parameter. And of course, we're just doing feasible path planning here. We're not doing shortest path planning or anything like that. So here is kind of how we're going to do this. When we kind of realize that we are close within this, this kind of ball radius, the forward tree has met the reverse tree, then we will insert the node into a priority queue. And then we're going to sort this thing based on the estimated distance if we connect, which is going to go from the start to where we are, plus little gaps to the other tree, and then the distance along that other tree to the goal. And we're going to pop things out of this and try to expand them. Here's the little blossom thing. We found our best kind of blossom, and then we'll do that, and then we'll quickly grow towards the goal, kind of using this strategy. And then in addition to this, there's also random sampling that happens occasionally based on that exploitation ratio. So we tried this on a number of different systems on the previous slide. So in simulation, we modeled all of these systems, and so the unicycle, the quadrotor, where we're representing those in 3D. Then the cart pole is kind of a 4-dimensional problem. Treaded 5D platform, car trailer, that's 6-dimensional system, and then a fixed wing aircraft is a 9-dimensional system is what we model that as. And kind of trying it in all of the different scenarios here. Here's just some videos of that working. Whenever they're done, it turns green. And you can see that it's very different types of systems that we use this general kind of bidirectional motion planning for. So it's a pretty general technique that could be used for a lot of different robotic systems. Here's some quadrotor experiments. Let's see if I play those like this. I don't have the sound on right now. Oh, I guess I do. Apologies. And these are experiments in our lab that Sharon ran, where we're getting around some obstacles. There's the pipe obstacle there and the pad obstacle, and also a net that's hung in the background. So to get through the obstacles, we have to go around some, both change in height and also kind of change in XY location with the quadrotor. And we're comparing just to simple RRT in this case. 5. Oh, now it works. That's good. So this is GAB RRT. This is where we are just using the kind of holonomic reverse tree as a focusing heuristic for the quadrotor forward tree. Okay, so that's kind of the end of the motion planning portion of this talk. Now I'm going to talk about swarms. There's also kind of motion planning, but now it relates to swarms. Oh, and I should say Sharon's work was recently accepted to the Transactions on Robotics, so we're very happy about that. This work is with my collaborators at the US Naval Research Lab, William McGuire, Don Sofjay, and Tristan Schuler. And this work was accepted to the Robot and Automation Letters a little while ago, and we just got to present it at ICRA last week. So the idea here is potential field methods is like a nice thing that many, I think, people can reinvent quite often. If they say, oh, I just want my robot to get to the goal, maybe I could model them as kind of charged particles where I have a negative charge and a positive charge, and then they'll attract each other. And if the goal's in the same spot, the robot will get attracted to the goal. But the problem with this is that, so here's kind of this, like, high potential, low potential. You move from the, from the goal, sorry, towards the goal from the start. You're kind of pushed that way like a charged particle. You can also model the obstacle using this potential field. So you're pushed away from the obstacle. It'd be like having a negative robot and a negative obstacle. They're going to repel each other. But when we sum these two fields, obviously we can get a local minima, which means that we can get trapped without actually getting to the goal. And this is like the Achilles heel of potential field methods, widely known. If you do take the time to do a literature search when you reinvent the wheel here, then you will find out that, oh, there is this problem. We can get stuck in a local minima. And so this work is saying, well, maybe if we have a swarm of robots, there's some hope to kind of having them communicate to overcome some of this. I didn't do a very good job of getting these movies to play, but we can do it this way. So here we see we have a number of robots that are trying to get from the left side of the screen to the right side of the screen, and a few of them get kind of trapped in this local minima. They're using the potential field method based on the fields that we just showed, and a couple of robots get there, but the other robots kind of get stuck. The robots are kind of repelling each other so that they don't have robot-robot collisions. So we said, well, if we have a lot of robots, swarms can have a lot of robots, maybe that can kind of save us. And the idea is that if we have enough robots that we can kind of fill up the space, like we're filling it up with a bunch of particles, then if some of those robots find the goal and they are within communication kind of connectivity of everybody else, they can tell everybody else, hey, the goal is in my direction, come towards me and you will get to the goal. So the way that this works is just based on a very simple kind of queuing idea where the first robot in the goal says, hey, I'm in the goal, I'm number one. If you are some robot and you can hear number one, then you become number two, and kind of et cetera. Any robot that can, the lowest number robot that they hear is number two becomes number three, et cetera. And if you have a couple of different equally kind of discrete distance away from the goal and in number of communication hops robots, then the robots are going to link to the robot that has the lowest distance. So the 7 here is linked to the 6 robot that's the closest 6 robot. And then we're going to use the neighbor that is kind of the parent in this tree structure to provide additional potential field force that will then tend to pull the robots around out of the local minima into the goal. And this is actually based on a physical sort of a system called Physioelastic Fluid, which is a self-siphoning fluid. And if you have a cup of this stuff and you pull a little bit out, it's kind of connected by a little slimy tendril to the rest, and it'll slowly siphon everything out of the cup. And so that was Loy's inspiration for coming up with this algorithm. And here's kind of a video of that happening. Oh my goodness. So this is our simulation. And a few of the robots get around, they get in contact with the goal, and then they're able to pull all the other robots out. More robots on this slide. And in this case, there's going to be so many robots that they can kind of go both directions around. And the goal is reached in 2 independent ways. And so that's how the robots are able to kind of go on either side of this thing. If there wasn't as many robots in the previous one, and so the robots that went over the top in the previous slide kind of found the goal first and siphoned the rest of the robots around to the other side. So we have, compared to Leonard Jones' potential algorithm and also this kind of just leader heuristic, and we see that if we have enough robots, then we can successfully get around the local minima. So one reason that we were interested in such kind of a nice and simple, easy to implement algorithm is in real life, sometimes we have swarms of actual robots, but we want them to kind of be doing something simple that we can understand so that it's intelligible to a human kind of what's going on. And we used the Georgia Tech miniature autonomous Blimp platform that was kind of my collaborators also collaborated with the creator of these blimps. And so we were able to do some hardware experiments. And here are the hardware experiments using the Blimp platform. So we have an obstacle set up. They know where the obstacle is, and then they're able to kind of funnel them around, and they get detached here. Oh, that's my timer to remind me that I'm just about out of time. And so we have implemented this on actual hardware, and Loy completely did an awesome job on these experiments. We put a ton of effort into them, and we have a lot of repeated trials of this working. So here are the hardware experiment data, and we see that with compared to the Lederer-Jones potential algorithm, the chain siphon algorithm is doing better. So that is it for that. And I would like to thank Fumin Zhang at Georgia Tech for designing these awesome robot blimps that we were able to use in our experiments. And that is the other collaborator of my collaborators at NRL, even though I'm not collaborating directly with Fumin Zhang. Definitely enjoy using his blimps. So that is it.
Any questions for Michael?
All right, well, thank you very much.